Hi everyone, we're going to get started on chapter 4 now. So this is all based on reactions in aqueous solutions. So we've seen that represented as AQ. So some substance dissolved in water can have that AQ as its state of matter. So like Na plus AQ, that's sodium ions dissolved in water. The first topic in chapter 4, identifying the correct sketch of a compound in aqueous solution. Before we go into that, let's set up some of these definitions here. So a solution is a homogeneous mixture of two or more substances. Remember, homogeneous mixtures from chapter 1, they appear the same throughout. But remember, for mixtures, they still retain, the components in a mixture still retain their individual identities. A solute, they are the substances present in the smaller amount. The solvent is the substance present in the larger amount. Usually, solutions we're used to hearing about is some solute dissolved in water, where water is our solvent. Then some substance dissolved, so the solute could be NaCl, where it dissociates into Na plus and Cl minus ions. Another example of a solute could be sucrose or sugar. So some solute dissolved in a solvent. Typically, water is a solvent. It's a very common solvent, at least in General Chemistry 1. There are some examples, though, of non-liquid solvents or non-liquid based solutions. We do have a soft drink where the solvent is water, and then the solutes, again, sucrose or sugar, and carbon dioxide gas. Another example, though, is air. So air is a solution. The solvent is technically nitrogen gas because that's what's present in the larger amounts in the atmosphere. Then the other gases that are present in air are oxygen gas, argon, and methane. So these are examples of solutes that are dissolved into our solvent of nitrogen gas because this is, again, present in the larger amount. Another example here is with metals. So if you've heard of a metal alloy, this is a solution, technically, of one metal and another metal. So if we're given this solvent, this is our solute, this is present in the larger amount, then this is present in the smaller amount, relatively speaking. Another feature of solutions, you should also feel really comfortable going from a formula into a name at this point. So this is potassium. MnO4 is permanganate. So either have those memorized or they're written on your note card to recognize this is potassium permanganate. This feature is showing this difference in color here. So the darker color means this is more concentrated and therefore has more solute dissolved into a solvent of water. So it's more concentrated, there's more solutes, this is less concentrated. There's less potassium permanganate in this lighter colored solution. So more concentrated, a more intense color, less concentrated, a less intense color, or a lighter color. What we're also getting into now in chapter 4 is on electrolytes. So you've probably heard of this in Gatorade. It's important to stay hydrated by drinking water with electrolytes. So an electrolyte is a substance that when dissolved in water, it results in a solution that can conduct electricity. That's technically the formal definition of an electrolyte. So it can conduct electricity. Whereas a non-electrolyte then is a substance that when dissolved results in a solution that does not conduct electricity. These are the technical definitions, and then we're going to go into what this means if it can't conduct electricity, or if an electrolyte in solution does conduct electricity. What's causing that electricity to be conducted? So we'll get to that on the next slide. Here's an example of what a non-electrolyte solution would look like then. Notice we don't have any light, so this did not conduct electricity. This solution did not conduct electricity. Within the category of electrolytes, we do have weak and strong electrolytes. So a weak electrolyte, you can see that electricity is conducted in solution, but not nearly as strong as the electricity conducted for a strong electrolyte in solution. So non-electrolytes do not conduct electricity. Electrolytes can conduct electricity when dissolved in a solution, and when dissolved in water here specifically. So what makes an electrolyte conduct electricity in solution? Well, it's the presence of these cations and anions that we've seen now throughout this semester of content. So in chapter 2 and in chapter 1 and in chapter 3, we have looked a lot at cations and anions. So the presence of cations that are positively charged and anions that are negatively charged, this is what causes the electrolyte solution to be able to conduct electricity. Coming back here, we looked at weak and strong electrolytes. Let's define these now as far as how they produce cations and anions in solution. A strong electrolyte will 100% dissociate into its cations and anions in solution. For example, sodium chloride is an ionic compound. When in the presence of water and it's forming a solution, it will completely dissociate into Na+ and Cl-. What I mean by completely dissociate is we are not going to have any NaCl on this side of the reaction, so on the product side. We won't have any NaCl left because all of it has dissociated into its cations and anions. The reason it is able to be a stronger electrolyte because this is an ionic compound, whereas weak electrolytes have incomplete dissociation of the original substance when dissolved in water. For example, we can have an acid like acetic acid. It will partially dissociate into this anion and this cation, so negatively charged and positively charged. But it's a weak electrolyte because on the product side, we don't just have anions and cations. Instead, and in addition, we have the anions and cations plus some of the original molecule here, or the original compound here. This is technically both a compound and a molecule because it's composed of 2 or more unique elements, so carbon, hydrogen, and oxygen. So we have dissociation into this anion, dissociation into this cation. So technically we will have anions and cations in solution, but we will not have complete dissociation. So on the product side, we'll still have some of this uncharged species. So this uncharged species will still be present on the product side, leading to some electricity produced, but not nearly as much, again, as the strong electrolyte. One thing I also want to point out here is why this does not further dissociate. Well, this is now composed of all nonmetals, making this molecular. Right, so remember the difference between ionic compounds and molecular compounds. Molecular compounds have all nonmetals. So now this will not further dissociate because this is not ionic. It does not have some metal species that will dissociate further into a cation and into an anion. So this portion here does not further dissociate because it's molecular. Why does this H+ dissociate then? Well, this is an acid. This is a weak acid, and we'll get more into this. For now, though, the takeaways are this difference between the strong electrolyte, so complete dissociation, versus a weak electrolyte, has incomplete dissociation into cations and anions. So again, weak electrolyte still has this original substance present on the product side of the reaction. So our original compound is here. Now it's technically in an aqueous solution, but it's uncharged. So now this concept of ionization was initially brought up very briefly in our discussion of mass spectrometry. So ionization of an acetic acid, let's go through this example. This is the one we looked at on the last slide. For an ionization, it's a process by which electrically neutral atoms or molecules, so notice this is electrically neutral, it doesn't contain a positive or negative charge, they're converted to electrically charged atoms or molecules, i.e. ions. So uncharged, and then these are the charged species. So charged species here, this is our definition of ionization, process by which electrically neutral atoms or molecules are converted into these charged atoms or molecules, i.e. ions, be it cations or anions. One thing I wanted to point out on this slide is this double-headed arrow here, and then notice for our ionic compound that's a strong electrolyte, it's a single-headed arrow. This means that NaCl will dissociate into Na plus and Cl minus ions, and it won't typically go the backwards direction where these ions will then reform the solid. So we would think of this single-headed arrow as an irreversible process. So irreversible, whereas this double-headed arrow here is a reversible process. It implies it can go the forward direction and the backward direction. So strong electrolytes typically associated with these irreversible reactions, weak electrolytes, these reversible reactions. So a reversible reaction, notice the double-headed arrow here in both the forward and the reverse directions. That means the reaction can occur in both directions. The correct way to show it is technically one full arrow in the forward direction and one full arrow in the backward direction. You may also see it represented like this. So just be aware that these are essentially the same thing for the cases that we're working with in the semester. We will get into where this implies resonance, and that will come up towards the end of the semester. We'll come back to this, but this double-headed arrow means it's a reversible reaction. And again, acetic acid is a weak electrolyte because its ionization in water is incomplete. So you still have some of this original compound or molecule present on the product side. And now it's in aqueous solution, like we saw on the last slide as well. So we looked at weak electrolytes and strong electrolytes. Then what makes up these non-electrolytes? So for these non-electrolytes, they do not conduct electricity. Why is that? They contain no cations and anions when in solution. How do we know if a molecular compound will produce cations or anions in solution? How do we know if a compound will dissociate into cations and anions in solution? Well, this is a completely molecular compound. It's completely molecular. There are no metals present. So no metals are present. This is not ionic. So for a molecular compound, there's no cations or anions to dissociate into. And more specifically, it's a molecular compound that's not an acid or a base. We'll talk about how to differentiate molecular compounds from acids and bases. For now, know this is not an acid nor a base, and it is a molecular compound, so it will not dissociate into any anions or cations in solution. So this molecule, which happens to be glucose, this will not further dissociate into cations and anions. This is why this is considered a non-electrolyte. So strong electrolytes, notice these ionic compounds, all these examples of ionic compounds. There's a typo here that I'll fix in the slides that I post for you. So this should just be HCl, right? This should be HClO4. It's important that that L is not capitalized, so I'll fix this typo in your slides. This too should be a subscript as well. So a connection we're going to make is that these ionic compounds are strong electrolytes. We're going to talk more about acids and bases, but also know that for a strong electrolyte, strong acids and strong bases are also strong electrolytes. So ionic compounds and strong acids and strong bases are all strong electrolytes. For the weak electrolytes, these are going to be our weak acids and weak bases. Again, we'll talk about how to recognize an acid versus a base within chapter 4. Hydrofluoric acid, you may have heard of from Breaking Bad, so this is a weak acid. although it is very detrimental to calcium in the human body. We just looked at this example. This is acetic acid. This is actually what's present in vinegar. So acetic acid is a weak acid. And so these weak acids and weak bases are our weak electrolytes. So they'll partially dissociate, but not fully dissociate into cations and anions. What about these non-electrolytes? These all have in common, they contain no metals, and they're all, therefore, molecular compounds. Okay, so non-electrolytes, you won't see any metals here present, carbon, hydrogen, oxygen, nitrogen, and they're all molecular compounds. We'll come back to what this is mentioning here on this sulfuric acid compound. It has two ionizable H+, making it a strong acid, but if only one of the H+ ions dissociates, then that's when we have a strong electrolyte. So only one of the H+ ions is totally ionized. We'll come back to acids and bases throughout chapter 4. So these molecular compounds, they will not dissociate into ions at all, so they're non-electrolytes, and we notice there are no charged ions present in the reaction. There's no charged ions here, and then more importantly, there's no charged ions here on the product side. It's just neutral. So as we're talking about solutions, we also need to talk about this idea of hydration, which is the process in which an ion is surrounded by water molecules arranged in a specific manner. So remember, for ions, we can have cations that are positively charged and anions that are negatively charged. Well, water is a special kind of molecule because it has polarity to it. It has this positive end and this negative end. This symbol notation means it has a partial negative. And this symbol notation then is a partial positive. These partial positive versus partial negative we'll also get more into. This is just a brief introduction. So partial is opposed to a full negative charge. So it's not a full anion, it has a partial negative charge to it from more electron cloud density surrounded by the oxygen atom. So red is the oxygen, and then these two white spheres are the hydrogen atoms. The hydrogens have a partial positive charge, not a full-on cation for a positive charge, because they have less electron cloud density around their atoms now. We'll get more into this throughout the semester too, so just if you're wondering what this partial negative and partial positive are, that's just a quick introduction. So in water, with these partial negative and partial positive charges, surrounds either a cation or an anion, let's notice what side of the molecule ends up surrounding itself with a cation. Well, here's oxygen with a partial negative, so it makes sense that the partial negative on oxygen will come closer into contact with the cation that's positively charged. This comes back to the idea that opposites attract or opposite charges attract. So for a cation, we notice the partial negatively charged oxygen is going to orient itself around that positively charged cation. Whereas for this anion, negatively charged, the partial positive hydrogens are going to want to be closer to the negatively charged anion. So those white spheres are those partial positives. So again, just coming back to the idea that opposite charges attract. So these partial positives will come closer into contact with the anion. And then you'll notice the partial negative on oxygen kind of reorients itself to be further away from that negatively charged anion. Okay, so partial positive ends are around the anion, whereas the partial negative ends are oriented around the cation more. This is how these different ionic compounds can dissolve so easily and so stably in water, because they form these very stable structures within a solution, so that cation then becomes surrounded by these partial negatively charged oxygen atoms in water. This is what's going on the molecular level of hydration. So now for the topic we're looking at, let's solve this practice problem based on everything we just went through for ionic versus molecular compounds and how they dissociate into water or how they don't dissociate into water. So we're going to pick the sketch that best shows what the solution would look like at the atomic or molecular level. The large number of faint red and white molecules in the background are going to be our water. And then we have these two compounds here. So let's talk more about, is this molecular? Is this ionic? How does that matter for the sketch in the end? So as we've been talking about so far, the really important key to solving a problem like this is distinguishing if we have a molecular or ionic compound present, because those will act differently when they dissolve in water. Molecular compounds, they break up into individual molecules. The molecules are made of atoms joined by chemical bonds, but these chemical bonds are very strong and do not break when molecules dissolve. The way that you can interpret this is they do not dissociate into ions. They do not dissociate into ions or charged species if they're a molecular compound. Now for ionic compounds, they do break up into their cations and anions from which they are originally made when they dissolve in water. So that means each formula unit, and remember for sodium chloride, that was one of your post-lab questions. Sodium chloride is the formula unit. It's in its simplest whole number ratio here. So that means each formula unit of the ionic compound comes apart into, in this case, Na plus and Cl minus. So now what we saw in chapter 2, though, is these are not always so straightforward, that we have this cation and anion, and they break up into their respective cations and anions. Instead, we did see that there are polyatomic ions. So let's focus on these polyatomic ions and how they play into these ionic compounds. Do they dissociate into ions as well? Let's see. So these polyatomic ions are like molecules in that they are made up of atoms joined by chemical bonds. These ions do not break up when dissolved. Like we saw earlier with potassium permanganate. Altogether, KMnO4, this is an ionic compound, right? It contains a metal and then a series of nonmetals. So this will dissociate into K plus and MnO4 minus. This is a strong electrolyte because it will completely dissociate into K plus and MnO4 minus. What's really important to recognize here with these polyatomic ions, though, like permanganate, is this permanganate will not further dissociate. So all of our polyatomic ions, they will not further dissociate, like permanganate, like ammonium, phosphate, all those examples. They might be paired with a metal cation, but the polyatomic ion itself will not further dissociate. I've been mentioning we're going to come back to acids. So acids are an important exception to this rule that molecules don't break up when they dissolve. Acids instead, they undergo a chemical reaction with water. As soon as they dissolve, that does break them up into ions. In our problem so far, just at the beginning of chapter 4, we're not really focused on acids and bases yet. So to summarize, molecular compounds will not break up into ions when dissolved in solution. That makes molecular compounds non-electrolytes. Whereas ionic compounds are strong electrolytes. They will break up completely into a cation and anion or a cation and anion in solution. But importantly to remember, with ionic compounds that are still strong electrolytes, but they contain a polyatomic ion, this polyatomic ion will not further dissociate. Okay, so it is going to be really important that you feel comfortable writing out names from chemical formulas or vice versa from chapter 2 moving forward. Because you will need to recognize we have an ionic compound that breaks up into cations and anions, or do we have a molecular compound? Okay, so for ionic compounds, it's a metal and a nonmetal. For molecular compounds, composed only of nonmetals. So for our two compounds we have, so CH3Cl and KCl. Let's talk about KCl first. So KCl is an ionic compound, right? We notice that this is an alkali metal, which will form K plus ions. This is a halogen, so will form Cl minus or chloride anions. So with a metal and a nonmetal, this is definitely an ionic compound. And because of that reason, this will break up into K plus cations and Cl minus anions. What we can also gather from this formula unit, right, so the simplest whole number ratio of those subscripts. So from the formula unit, KCl breaks up into one K plus ion and one Cl minus ion, one K plus cation, one Cl minus anion. This means the ratio of cations to anions in the entire solution must be 1:1. For a balanced reaction, this would look like K plus, and I should include the aqueous here, so K plus and Cl minus aqueous. There's a 1 molar coefficient here and a 1 molar coefficient here. That's implied. This is a balanced reaction. Whereas barium chloride, Ba would form 2 plus ions, Cl still -1, so BaCl2. If we write this out, where the formula unit is 1 to 2, this means we'll form Ba2 plus cations and Cl minus anions still, but to balance this, we have to write a 2 right here. So for every 1 ion of Ba2 plus, there are 2 ions of Cl minus. Right, for this formula unit though, we just had a 1:1 ratio. So here's our 1:1 ratio of this cation to this anion. So this formula unit helps us say the ratio of cations to anions based on these subscripts here. Because this is an ionic compound, because it contains a metal and a nonmetal, then because it's a strong electrolyte, we're going to see K plus and Cl minus ions present in a 1:1 ratio when dissolved in water. So this is definitely the right sketch here for KCl. What about this molecule here? So it contains carbon, hydrogen, and chlorine. Are these metals? Are these nonmetals? Well, these are all nonmetals based on their placement on the periodic table. Because these are all nonmetals, with all nonmetals, this makes this a molecular compound. For a molecular compound, we know these are going to be non-electrolytes and therefore will not dissociate. So they will not dissociate into their cations and anions when dissolved in water. What does that mean then? We'll have a carbon, 3 hydrogens, and a chlorine. It'll be in this form before it dissociates, and it'll still be in this form after it dissociates. So therefore it's not really dissociating. I should say this is before it's dissolved in water and then after it's dissolved in water. So CH3Cl will not dissociate because it's a molecular compound. It will stay intact. Therefore, this molecular compound will not dissociate at all in the presence of water molecules. So here's our carbon in the middle. Here's our 3 hydrogens, CH3Cl. So there's 1 carbon, it's in the middle. We know there are 3 hydrogens, so these 3 yellow spheres must be the hydrogen. Then this green sphere must be the chlorine. So we notice these chemical bonds are very strong and do not break up at all when these molecular compounds are dissolved in water. Whereas for ionic compounds, they're not really held together by real bonds, right? So Na plus and Cl minus, this ionic bond is in quotes here, right? It's more of an electrostatic attraction or electrostatic interaction. So because these ionic compounds like sodium chloride and potassium chloride are composed of ionic bonds, they have an electrostatic attraction, and so they can more easily dissociate when dissolved in water. But for a molecular compound, it's not ionic bonds that are holding this together, it's actual covalent bonds. So ionic bonds here, more of an electrostatic interaction or attraction, and these are covalent bonds that are real bonds between these atoms. We'll come back to structures and bonding later on in the semester. The next topic here in chapter 4 is predicting precipitation. So when a precipitate is formed, we define this as an insoluble solid that separates out from solution. Here's a very pretty example of this yellow precipitate here made of lead and iodine. So precipitate, it's the insoluble solid that separates from solution. Insoluble here, if something is insoluble, it won't further dissolve in solution. So it stays as this solid or semi-solid here, and it separates out from the rest of the solution. So in forming precipitates, we're going to end up writing out these reactions where we take into account the different species that are involved. Then we predict from the different species that are involved, can a solid insoluble precipitate form from this combination of species that are present? So this is our molecular equation because we're going to write out all the species and their compound and their molecular form. Molecular form means we don't yet see all these charges here like we see in the ionic equation. So for this molecular equation, we do not see any of the charges. So here we see the reaction written out as such, and we see the solid forming. Now, what we're going to get into is going from a molecular equation like this into a net ionic equation or ionic equation. So we're going to get into both of these. So let's go from a first molecular equation to the ionic equation. Then we'll talk about how we go from this ionic equation to the net ionic equation. This ionic equation takes each individual species and actually shows them as their respective ions. This means we also need to be really comfortable writing out what ions can each atom or each element form. Lead 2+, nitrate, this is a polyatomic ion with a -1 charge. It's going to be necessary that you're comfortable recognizing this. Sodium as an alkali metal forms +1 ions. Iodine as a halogen forms -1 ions. Okay, so from the replacement on the periodic table and having those polyatomic ions memorized or handy, now we're going to write out each species in its respective ions. One important detail here is for this to be balanced, we had 2 Na and 2 I. So notice this coefficient of 2 for the Na and 2 for I. Then on this side, we still have the ions that are present. These are the ions that are not involved in forming the precipitate. So sodium and nitrate don't make a solid precipitate. It's the lead and iodine that do. We'll get into how we predict that lead and iodine will be an insoluble precipitate. So for these on the product side, we either have this solid or we still have the ions that are present now on the product side. These again are the ions that were not involved in forming this solid precipitate. Now, for the net ionic equation, this is when we cancel out any species that appear in the same form on both sides of the reaction. So these over here were the ones not involved in forming the solid precipitate, so they're present on both sides of the reaction. Therefore, we end up canceling these out and writing out our net ionic equation. To clarify, this is still the ionic equation without these x's here, right? So this is the ionic equation. Now we're just showing that we're xing out some of these to go to the net ionic equation. In the net ionic equation, we only have the species that are composing the solid precipitate, and they're in their balanced form. So 1 lead ion and 2 iodine or iodide ions here make up this lead iodide precipitate. Now to write out the full name for this, I should say lead 2 iodide. Why do we need that 2 there? Well, lead can form 2 different kinds of ions. Here it's in its 2+ charge. So from that periodic table, we know that lead can form 2+ and lead 4+ cations. So because here it's a 2+ charge, the full name would be that lead 2, Roman numeral 2, iodide. So if a metal can form 2 different kinds of ions, we need those Roman numerals here, going back to naming in chapter 2. The other important piece of terminology here are these spectator ions. So here's sodium and nitrate. They're not part of forming the solid precipitate. We end up canceling these out here. So the technical name for these are our spectator ions. Let's take a look at the molecular level or the atomic level of what's happening when a solid precipitate is forming. So from the net ionic equation, we know we're just going to have lead and iodine go on to form this solid precipitate. This is a slightly different example. Now we have potassium iodine here instead of sodium iodine. Still the same principle here. So we have potassium ions present. We have nitrate ions as well, but we know those are going to be spectator ions because the only ions involved in forming the precipitate are again lead and iodine. These red and white molecules are again our water. So this is all happening in an aqueous environment. So based on the properties of these 2 ions, when they come together or they're in close enough proximity in solution, this solid precipitate will form. This whole precipitate is insoluble. So it's an insoluble, solid, or semi-solid. So here this insoluble precipitate forms. It's a solid, so its atoms are closer together. And that's why it's insoluble now, and that's also why we can now see it visually. So it's no longer floating around in aqueous solution. Those ions come together to form this semi-solid precipitate that we can actually visualize now. So you may be wondering, how am I supposed to know that when lead comes together with iodine in its 2+ form, so lead in its 2+ form, how does this form a solid precipitate? How would I know that? Then also, how would I know that these are going to be spectator ions? Well, there are a few charts we're going to look at to make this connection. This chart is a chart of our solubility rules. This is going to be a really important chart to keep in mind for chapter 4. So there's this presentation of the solubility rules. I've also included this presentation as well. So why would lead and iodine come together to form a solid precipitate? How could we use this chart to show us that? So here we see the halides or the halogens, but in their ionic form. So these halides, chloride, bromide, iodine, when any of these halides is paired up with silver, mercury, or lead, it becomes insoluble. That's how we know that Pb2+ and I-, when they form together, make an insoluble precipitate. What else can we notice here? Well, if we have lead with sulfate, that is also insoluble. What about lithium, sodium, potassium, some of these alkali metals? anything containing these alkali metals or the ammonium cation are going to be soluble based on these solubility rules. What about down here? Well, this looks like any carbonates, phosphates, or chromates or sulfides. These are insoluble except when they're compounds that contain an alkali metal or the ammonium ion. So these are always insoluble except when paired with an alkali metal up here or ammonium. Hydroxides are always insoluble except these soluble exceptions that all the hydroxides are insoluble except compounds containing alkali metals again or barium 2+. So the way to read this is barium 2+, meaning for the cross method, we have Ba2+ and OH-. That 2+ comes down here, -1 here, to make this chemical formula of BaOH2. This chart is saying that it contains hydroxide, so you might think it's insoluble, but these soluble exceptions include barium. So barium and hydroxide, this whole thing is soluble. If hydroxide were paired up with an alkali metal as well, that would also be soluble. For all the other cases, hydroxide will be insoluble. You should write some form of this chart and these solubility rules on your note card. So another representation of these solubility rules, you might like this version better. It's sort of a combination of some common ions and solubility rules to be aware of. Something to also point out here, as it says soluble, this remains in its ionic form in an aqueous solution, and the species are denoted as AQ, like we saw for Na+, aqueous, and Cl- aqueous. When you see soluble in the charts, know that these dissociate into their respective ions. They're soluble in water, and then they're in their aqueous state of matter. Whereas insoluble then, how do we read that? If it's insoluble, it forms a solid or semi-solid precipitate that we denote as S. So for example, we had lead and iodine. I wanted to make this balanced here because then we do, to show this written out, if we do the cross method, then this is Pb with 1 and I with 2. So then this simplifies into PbI2. Using this chart, we can also see when we have iodine ions present, the rule is that these ions are insoluble with silver, mercury, or lead. So this is insoluble, meaning we need to denote this with an S here. So let me finish writing this one out. So Pb2+ and I2-, these come together to form PbI2 as an insoluble precipitate. And therefore we denote it, importantly, with this S here to be a solid. Okay, so these charts are really helpful as long as you're comfortable reading them to see, like lithium and sodium, they're always soluble. So being able to differentiate when they're soluble versus insoluble. It can get a little confusing to read, but as you start to get more familiar with them, they end up being really helpful in helping us write out different precipitate reactions. Here's another example of these precipitates that can actually be really pretty in solution, as you can see with these different colors. So as a challenge here, based on the solubility rules on the past 2 slides, can you confirm that when these ions come together, they will form an insoluble precipitate? So be sure to try this exercise and prove to yourself that these would form insoluble precipitates. And try to write out the full reaction too, the full balanced reaction. So the different ions on the reactant side forming some insoluble precipitate, and make sure the molar coefficients lead to a balanced reaction. Also, for more practice, try naming all of these as well. So practice writing out the name and these reactions, and let me know if you want to talk through any of those. Let's try this practice problem now. We're going to look at solution A and solution B coming together in solution, so in an aqueous solution. Then we're going to predict if a precipitate will form when A and B are mixed, and then if so, we're going to write out the empirical formula of that precipitate. To solve problems like this, we're going to take them on very systematically. So when solutions contain cations and anions that can form an insoluble precipitate, it's when they form an insoluble ionic compound. So this is technically an ionic compound, right? It contains a metal and a nonmetal. This is an insoluble ionic compound. So you may be wondering, coming back to this, if you're making this connection, that ionic compounds are strong electrolytes. Well, for an additional level of complexity, if an ionic compound is insoluble, then technically it's not a strong electrolyte, right? Because it won't dissociate into its respective cations and anions. So this is an exception to the rule that does add this layer of complexity. So technically this is an ionic compound, but it's insoluble. So this would actually not be a strong electrolyte. Okay, so to clarify that point, this would not be a strong electrolyte. Although it is an ionic compound, it forms this insoluble ionic compound. How would we know that silver and chloride coming together forms this insoluble precipitate based on those solubility rules? Well, this row looks helpful. So here we have chloride ions. They are insoluble with silver. So there we go right away, silver and Cl. This forms an insoluble precipitate. So insoluble precipitate because we see Cl minus is insoluble with this ion of silver. That's how we know when silver and chloride get together, they're going to form this insoluble precipitate based on the solubility rules. The first thing we needed to do was take, for example, the name silver chloride. From there, we write out their respective ions. From there, we can see if the respective ions, based on the solubility rules, will form an insoluble precipitate or if they'll be soluble. In our practice problem, we have a mixture of ionic compounds where A contains a cation and an anion, and B does as well. So we're going to match up and see if any of these cations with any of these anions will form an insoluble ionic compound, or therefore if they'll form a precipitate. There's no real foolproof way in knowing if they're going to form an insoluble or soluble precipitate. What we will work from are these general solubility rules. These do work in most cases, and this is another representation of those solubility rules. This table was provided by Alex. So for all these table representations, figure out which one you are comfortable working with, which one you're comfortable looking at to say, okay, nitrates are always soluble, chloride ions are soluble except with these exceptions. So it's just different representations of essentially the same information. So I mentioned that A and B are both composed of a cation and an anion. So to solve this problem, we need to figure out every possible cation-anion combination, then decide if every possible combination is soluble or insoluble based on the solubility rules. Let's go through the first question here in our practice problem. Here we have iron 3 chloride and potassium hydroxide. The very first step is to take these names and write out the chemical formulas. So iron with Roman numeral 3 means iron 3 plus. Chloride, it's a halogen, Cl, it always makes -1 anions. Or it most stably makes -1 anions. So when these come together using that cross method, FeCl3. FeCl3, we know that as its name of iron 3 chloride. Importantly, the Roman numerals are completely necessary because iron can form two different kinds of cations. either 2+ or 3+. Here it's formed 3+ cations. Potassium hydroxide, to name this, potassium is an alkali metal. It forms +1 cations. Hydroxide should be a polyatomic that you have memorized or you have accessible to you. So hydroxide is OH-. Using the cross method here, we would end up saying 1 and 1. So we just write this out as KOH. We don't need the parentheses here because that subscript is just 1. Let's go ahead and write out all the ions that make up the rest of our solutions. Then we'll continue solving the problem. Sodium chloride, that's going to be Na+ and Cl-. Barium bromide, barium will form 2+ ions because it's an alkaline earth metal. Bromide is a halogen, so it forms -1 ions. Again, it's really important that you feel comfortable going from names into the respective ions and names into formulas here as we continue on with chapter 4. What about sodium and iodine? Here, this is Na+ and I-. Right, this is an alkali metal, this is a halogen. Lead to nitrate now. So either we have nitrate memorized or we're able to look it up quickly. So lead is Pb2+, nitrate is NO3-. We know it's 2+ because of the Roman numerals here. We had to include the Roman numerals in the name because lead can form either Pb2+ or Pb4+ ions. Here we're told it forms Pb2+ ions because of the Roman numerals there. Then nitrate is NO3-. Again, having that memorized or just having that really accessible to you, like on your note card, for example. Going back to solving our first practice problem now, we know we have our iron, chloride, potassium, and hydroxide. Now let's continue on. To find every possible combination of cation and anion, we can write out something like this. So here we have iron 3+ and potassium+, Cl- and OH-. Here are all of our cations in this mixture of A and B. Here are our anions. Now with this kind of table, we can say, is Fe3+ and Cl-, is that an insoluble or soluble combination? Well, let's look at this table now. Let's look at this representation to get comfortable here. So this is the one in your book. So Cl-, these are soluble compounds except when they're with silver, mercury, or lead. Well, that's not the case here. It's with iron. So Cl with iron is going to be soluble. So Cl with iron is going to be soluble. Cl with potassium is also soluble because potassium is not one of the insoluble exceptions. Right? Potassium is not listed here as one of the insoluble exceptions with chloride. Let's do the next soluble one. So let's do potassium with hydroxide. Then we'll also need to look at hydroxide with iron 3+. So here's potassium. Compounds containing alkali metal ions potassium are always soluble. So potassium hydroxide then is also going to be soluble. The next one though, so OH-, but with iron 3+. Now let's look at this portion here in our solubility rules. So for hydroxides, these are generally insoluble, except with compounds containing alkali metal ions like potassium, therefore proving that hydroxide and potassium are still going to be soluble. Right, so we looked here, we could have also looked here on the table. So now let's look at hydroxide and iron 3+. Hydroxides are generally insoluble. Is iron here listed as one of the soluble exceptions? Well, the soluble exceptions with hydroxide are the alkali metal ions and barium 2+. This means that this combination is going to be insoluble, right? Because iron is not listed here as one of the soluble exceptions. Therefore, iron with hydroxide, we do note that this becomes an insoluble precipitate. To write out the formula here, this is iron 3 plus, this is OH minus. To write out the formula unit here, right? Formula units are for our ionic compounds. Iron is a metal, so this is an ionic compound. With the cross method, this would be iron and then parentheses OH subscript 3. So FeOH3 to write that out more clearly. So FeOH3 is going to be our insoluble precipitate. How do we name this then? Let's practice that. This is iron in its 3 plus state, so we have to write out iron Roman numeral 3. This hydroxide is a polyatomic anion, so we don't change the name, we just leave it as is. So iron 3 hydroxide. So iron 3 hydroxide. Now let's continue on to the next set of problems. Here we have Na plus, barium 2 plus as our cations with chloride and bromide. Let's check out chloride and bromide and see if sodium or barium fall into any of the insoluble exceptions. So here's our halides. We have chloride and bromide. The only insoluble exceptions are silver, mercury, or lead. Here we do not have silver, mercury, or lead, so all of these combinations with our halides of chloride and bromide are soluble. These are all soluble in solution. Nothing will form an insoluble precipitate. The next combination of ions here, we have sodium iodine, lead, and nitrate. To set up this table, we have our cations again, and then our anions. We do know for this halide of iodine that sodium is not an insoluble exception, so with iodine, sodium will be soluble. What about sodium with nitrate? So here's sodium. Compounds that contain the alkali metal sodium are soluble. So anything with sodium is going to be soluble. So anything with sodium is going to be soluble. Now we need to look at lead and iodine and lead and nitrate. I should say we need to look at lead 2. So lead 2 plus with iodine and with nitrate. So here's lead 2 plus. So I minus is soluble except when it's with lead. So iodine and lead together is going to be an insoluble precipitate. What about nitrates? Well, these are always soluble. So even lead with nitrate is still going to be soluble. So here we get lead with nitrate, still soluble, but lead with iodine, insoluble. Looking at this form of the table, the solubility rules, nitrate, always soluble. I minus with lead, though, is an insoluble exception. So looking at either table again, and this one as well, and this one as well. So find a table you feel comfortable looking at to then describe the soluble versus insoluble combinations. So here to name this insoluble precipitate, we have lead 2 plus and I minus. To do this sort of cross method, 2 comes down here, 1 here. So we don't include that 1. So we say this is PbI2. How do we name this? Well, this is still lead 2. We have to include that Roman numeral here because lead can form either 2 plus or 4 plus cations. Then I minus, we change the ending to IDE because this is a monatomic anion. So iodine becomes iodide. If it were a polyatomic anion, we would keep the name of the polyatomic anion as is, like we did for this example. So hydroxide is the name of this polyatomic anion. In the name, we just write out that polyatomic anion. We don't change the ending. This one does already happen to end in IDE. If it ended in something else, again, we would not change the name for those polyatomic ions. So here we had, does it form a precipitate? Yes, yes, and then no. For our no answer, we couldn't write any empirical formula in. For our yes answers, we could. So iron 3 hydroxide and lead 2 iodide. Okay, so be able to write out the formulas and also be practicing naming still. Into chapter 4, be sure you're keeping up with naming and keeping that fresh. So FeOH3 with the parentheses here and the 3 on the outside. That's our answer here. Lead 2 iodide, here is our answer for that one. So now we have our final answer here. Again, naming, writing out formulas, getting really comfortable looking at the solubility rules is going to be important here in these topics in chapter 4. There's another example you can look at in the main slide deck for more practice on this as well. Now, using all this information we've gone over in chapter 4 so far, we're also going to come back to this idea of writing net ionic equations. We looked at this towards the beginning. Now we're going to practice doing those steps to actually write out the net ionic equation. We looked at it just briefly. Now we're going to go into the full details of doing this. So for writing out net ionic equations, we're going to follow these steps. First, we're going to write out the balanced molecular equation. Remember, the molecular equation is to write out the species in their compound and their molecular form. Really importantly, for these molecular equations, we're sticking with neutral charges. We do not show the respective ions yet in their charged form, so everything is neutral here in our molecular equation. Next, write out the ionic equation showing the strong electrolytes and completely dissociated into cations and anions. So in step 2, we're not yet considering soluble versus insoluble electrolytes, or soluble versus insoluble ionic compounds. We're going to take every compound that's there and try to write it out into its cations and anions. If it's a molecular compound, then we can't write it out into its cations and anions. For every other species, though, we're going to write it out into its cations and anions. Then we'll consider the solubility. So after you write out the cations and anions, then this step here is to consider the solubility. You can combine these two into one step. We're going to practice it as we're writing out the ions into cations and anions, then considering what's soluble and insoluble, then go on to step 3, where we cancel out the spectator ions that are present on both sides of the equation, where the spectator ions are not part of the solid precipitate. So if they're not part of this insoluble precipitate, they're part of the soluble form, then we end up canceling those ions out as spectator ions. What's left is going to be our net ionic equation, where we've canceled out species that appear in the same form on both sides of the reaction, and we're just left with the ions that form a solid precipitate. So it's only the cation and anion that form the solid precipitate plus the solid precipitate itself. So these cations and anions that form the solid precipitate and the solid precipitate are what we're going to see in our overall net ionic equation. Then before it's our final answer, we are going to check that the charges and the number of atoms are balanced in our net ionic equation. Let's execute these steps in a practice problem. Here we're asked to write out the net ionic equation for this reaction. An alternative way you may be given a problem is given the names, and then you'd have to write out the names in the reaction form. So we have names into their compounds. So if we were told, for example, that tin 2 chloride reacts with sodium hydroxide, we would need to be able to write out the formula for tin 2 chloride and sodium hydroxide even from the names. So from the names, you should be able to write out these different formulas as well. Here in this practice problem, we're given this reaction, which already contains the chemical formulas. So now we're going from there, but do feel comfortable starting with names here as well, instead of the full compounds already written out. So before going into writing out the net ionic equation, I want to give a little bit more background, then we'll solve it. So an important fact about aqueous solutions is that an ionic compound present when it's dissolved will not be present as whole formula units, but instead as separated ions. Remember, we won't see NaCl present in its whole formula unit. Instead, we'll see Na plus ions separated out from Cl minus ions. So that's this example here. We're not going to see NaCl formula unit present. Instead, we'll see it as the Cl minus anions and the Na plus cations. So we may be told sodium chloride. From there, we know we could write out the name of NaCl, but from what was just mentioned on the last slide, we know that NaCl won't really be present as NaCl. Instead, we'll start to think about this as being Na plus and Cl minus ions that are present in solution. And now this difference here on ionic equations versus molecular equations that we've looked at just briefly. So ionic equations, it's the equation that describes an aqueous chemical reaction with each ion shown separately. Versus a molecular equation is the equation which shows the ionic compounds as if the formula units were still together. This is called a molecular equation. We see only neutral charges here for our molecular equations. For ionic equations, though, we're going to see each ion shown separately, so cations and anions. To then go on to find our total ionic equation from a molecular equation, we're going to replace each dissolved ionic compound with its respective ions that break up when it dissolves. That it breaks up to when it dissolves. So here we were not starting with names, but we could also go from names to then writing out these compound formulas or these chemical formulas. Now we are starting with this, so the first step we need to take is to write these out into their respective ions. Again, I'm highlighting here how important it is to be able to write out names from formulas and vice versa. Some more review from chapter 2. So here's tin. From the periodic table that shows the different ions that can form from each element, tin can form either 2+ or 4+ ions. Well, here in this formula, how do we know whether it's 2+ or 4+? SnCl2, we know that chloride always forms -1 anions. So for sort of the reverse cross method, if the final formula is SnCl2, this means that tin needs to be in its 2+ form because here chloride is -1. And predictably, always chloride is going to be a -1 anion as a halogen. So from this formula, we have tin 2+ and Cl-. Really importantly though, to make this balanced, there are 2 Cl's here, so we do have to include 2 as the molar coefficient there. Now we've broken up SnCl2 into its respective ions. Importantly, it was 1 Sn2+ and 2 Cl-, so we had to include that molar coefficient of 2 here. Next, let's look at the next reactant. For sodium hydroxide, sodium is an alkali metal. It prefers to form +1 ions. Hydroxide is a polyatomic anion that you have memorized or have access to, where this hydroxide anion forms -1 anions, or it has a -1 charge here for hydroxide. So importantly, if we're given names and we're writing out the formulas, we're also balancing the reaction. So not only are we feeling comfortable writing out the formulas from names, but also balancing reactions at this point where we needed a 2 here and a 2 here for all this to be balanced. Because this is the 2 molar coefficient, and we decided sodium hydroxide is broken up into Na plus and OH minus, then for the respective ions here, we have Na plus and OH minus, but super importantly, we have this 2 included out front for both of their molar coefficients. Then the other detail to point out at this point is we have all these in aqueous states of matter because they're in water, they're dissolved in water. Now for our products, we need to break up these ions, except we don't need to worry about breaking up the solid insoluble precipitate. For this insoluble precipitate, we just leave this as a solid. It's not worth writing this out into its respective ions because this just comes back to form an insoluble precipitate from its respective ions. Just for practice, if we have OH minus, but then the total formula here is SnOH2, that means that again, tin is going to be a 2 plus charge because then with the cross method, we have SnOH2. Again, not worth writing out Sn2 plus and OH minus into the respective ions in an aqueous form because they come back to form this insoluble precipitate. What we can break up into its respective ions is this aqueous solution here. So sodium chloride gets broken up into Na plus and Cl minus. Again, because this 2 is out front here, we do need to put a 2 for the molar coefficient here and a 2 for the molar coefficient here. In our initial problem here, we were told this is aqueous, aqueous, solid, and aqueous. You should also feel comfortable going from names to compounds to balancing the reaction to then also predicting, is this going to form a solid insoluble precipitate, or are these ions going to come together to form a soluble aqueous compound like sodium chloride? Here we're told this is forming an insoluble solid precipitate from Sn2 plus and OH minus. Let's be sure we are comfortable proving this as well using those solubility rules. So for OH minus, these are insoluble compounds, and tin here, Sn2 plus, is not listed as a soluble exception. So indeed, Sn2 plus and OH minus come together to form an insoluble precipitate. So we could also predict that chemical reaction, that these are going to come together to form an insoluble precipitate just based on the ions that are present in that reaction. So now we're at this step. We have all these ions broken up except for the insoluble solid precipitate. The next thing to do here is to figure out what shows up on both sides of the reaction, which makes those ions our spectator ions. So if they show up on both sides of the reaction, it means they don't participate in the chemical reaction where a precipitate is formed. We're only focused on what forms that solid precipitate. So these spectator ions are non-participating ions. They have to show up in their same form on both sides of the reaction. What I mean by that is 2Cl minus in its aqueous form, 2Cl minus in its aqueous form. This gets canceled out, and this gets canceled out. Sn2 plus aqueous, does that show up over here? No, it doesn't. Sn2 plus aqueous is on the reactant side, but now tin is involved in the solid precipitate. These are not the same forms of tin, so we keep tin in our full net ionic equation. 2Na plus aqueous, that shows up here. 2Na plus aqueous, that shows up in its exact same form on the product side. 2OH minus aqueous, do we see that in its aqueous form on the product side? No, we see it in its solid precipitate, so we keep this as well for our net ionic equation. So for our net ionic equation, we're looking for that solid precipitate on the product side. On the reactant side, we're looking for the ions, one cation with an anion, that end up forming the solid or insoluble precipitate. I keep saying solid, insoluble precipitate because remember the precipitate is insoluble and it's a solid or semi-solid, so it's a solid but insoluble precipitate. Because it's insoluble, that's why it shows up as a solid in solution. So what's left here is what we call officially our net ionic equation. We canceled out the spectator ions. We're leaving just what forms the solid precipitate. So the ions that go into forming the solid precipitate. This is ultimately our net ionic equation. It ends up not mattering technically that we had Na plus and Cl minus ions in solution because those were not involved at all in forming what we're interested in. So we're interested in seeing what forms the solid precipitate, which in this case is tin 2 plus and OH minus. So this is our net ionic equation. As a reminder here, if something is soluble, it remains in its ionic form, denoted as AQ with the charge, be it a cation or an anion. Whereas an insoluble, something that's insoluble, it forms a solid or semi-solid precipitate, and the species are denoted by that italicized S here to represent solid or semi-solid in this case. One thing to also point out here is the reverse reaction. Notice we have the solid precipitate going into its aqueous ions. The exact reverse of forming this solid precipitate is when we dissociate the solid precipitate. And when we dissociate the solid precipitate, this is what's known as it dissolving or going into solution. For insoluble precipitates, it's much more difficult to have this solid precipitate break up into its respective cations and anions. If we are able to get it to dissolve, it will dissociate back into its cations or anions, but not very easily because, again, these ions coming together naturally form an insoluble precipitate. So for an insoluble precipitate, these ions will not form or reform as easily compared to a soluble compound like NaCl. If you take solid salt or solid sodium chloride and you put that into solution, these ions will easily and naturally form in solution. So because it's soluble, we'll more easily see these ions reformed in solution relative to its insoluble counterpart or an insoluble precipitate, like tin 2 hydroxide. Okay, there are usually more examples in the main slide deck. If you want to see some more practice, also let me know if you have any questions. I'm going to also include some animations here, so hydration and more on electrolytes. I hope you're all doing well. I'll talk to you next time for Chapter 4A, Part 2. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the Zoom button to view sodium chloride dissolving in water on a microscopic scale. Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
An electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. The light bulb will light if a substance is an electrolyte. Sodium chloride, NaCl, is a soluble salt that is assumed to completely dissociate into ions. NaCl is a strong electrolyte when dissolved in water. The solution contains a large number of ions, and the light bulb is brightly lit. Polar water molecules interact with the positive and negative ions of the salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between the water and the salt ions causes the salt to break apart or dissolve in water. Hydrofluoric acid, HF, is a weak acid which only partially ionizes in water. HF is a weak electrolyte. The solution contains only a small number of ions, therefore the solution is weakly conducting and the light bulb is dimly lit. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ion, F-. Methanol, CH3OH, does not dissociate into ions when dissolved in water. It is a non-electrolyte. A non-electrolyte solution does not contain ions. Therefore, the solution does not conduct electricity and the light bulb does not light. Methanol molecules contain a polar OH group. The oxygen has a partial negative charge and the hydrogen has a partial positive charge. This charge separation is called a dipole. Methanol molecules are attracted to each other through the interaction of the dipole of one molecule with the dipole of another molecule. Water is also polar and the dipole of water will interact with the dipole of methanol. These particular dipole-dipole attractions are called hydrogen bonds. The attractions between water molecules and the methanol molecule will break the attractions between methanol molecules, causing methanol to dissolve in water. Note that upon dissolving, the covalent methanol molecules remain intact. Compare this to the dissolution of an ionic compound such as sodium chloride, NaCl, which breaks apart into its component ions in water.